So welcome back to Lecture 5B. Here we're going to do just a little bit of applying symmetry and see if we can figure out what symmetry label we would apply to a p orbital on a water molecule. So if we look at water, we go through the point group determination that we learned last week. We would see that it has a symmetry group of C2V. If we pull up the character table for C2V symmetry, we see these functions here. So we have our symmetry operations here and these irreducible representations. Now, it doesn't mean that all of these apply to water. There's other things that are C2V that might apply differently. So we have to look at each molecule separately to see how things might apply. So character tables are listed online. Several books have them in the appendix if they teach this material in their content. A normal first-year book would not have this material in there. However, you can look up an inorganic chemistry textbook as a good example. They would generally have character tables in the appendix in the back. So now we're going to look at a py orbital on the oxygen atom that sits in the center of our water molecule and see if we can figure out which of these labels would apply to that particular orbital. We're going to go through each symmetry operation. So we'll go through E, then C2, sigma V, and then the other sigma V. So here you actually see which plane the sigma V is in. So remember, this is a reflection plane that is parallel to the primary axis of rotation, but they give us the plane. Sometimes this would just be sigma V, and this would be sigma V prime. So what we'll find here is whichever line A1, A2, B1, or B2 is fully filled in at the end, that is the symmetry of the orbital. It's a little bit more complex, and it's a very stepwise process here, but when we're learning how to do this, I find it works fairly well. So here we have our water molecule. We have our p orbital here, so this is the py, our little red line here. So this is our primary axis of rotation. We do have a C2 axis of rotation. By definition, this axis of rotation is the z axis, and so this is our z axis. And so I just picked this as the y. Could have called it the x, but I find it works better with the character table here if it's a y. And so here we have our first operation, the E. And so anytime you have this E operation, everything is always 1, because remember, our E operation is the identity operation, so the molecule remains unchanged. And so this p orbital remains unchanged here. And so everything here is 1. Okay, so that was a C2 operation. Notice that I rotated my molecule 180 degrees. This was blue, and this was red. And so we still have a p orbital in the exact same place. However, it has changed its phase. And so this tells me that I have a -1 character for that operation for the C2. Okay, so the py orbital has a -1 operator. Well, that means that the py cannot be A1 or A2, because A1 and A2, I should have a character of 1, but I don't. And so it must be a B1 or a B2 symmetry, because these both have a -1. So it fits the E and it fits the C2 for both B1 and B2. The next one we're going to do is the sigma V in the XZ plane. So since this is our Y orbital, the XZ plane is going to, well, we'll see it in the next diagram. It's going to fall like that. So it cuts the molecule in half, and so we go here. So if I were to reflect this molecule from side to side, the blue would move over here and the red would move over here. So it has pretty much the exact same effect that a C2 operation has, except now it's a reflection through this mirrored plane. And because the blue becomes red and the red becomes blue, I have changed my phase. And so that means that I have a -1 trace for this operation. So I have a -1 and a -1. And now we'll look at our final one, which is a sigma V in the next plane. And so here I have another reflection plane, which is parallel to the molecule here. It doesn't cut it in half. across the short axis, it cuts it in half on the long axis. And so when I reflect through this plane, I'm just taking this half of the blue and putting it onto the other half of the blue, so blue is still blue. Same with the red lobe of the p orbital. The red lobe of the p orbital reflects onto the back of the other lobe of the p orbital, and so I have red onto red. So the trace here would be a 1. So I would have a 1 character. And so notice now that because I have for B2, I have a 1 for the E, -1 for the C2, -1 for the sigma V, and a -1 for the sigma V prime. All those operations apply to that py orbital, so I know my py orbital has a B2 symmetry within the C2V character table.